Okay, it looks like a couple people have answers, and they're correct. It's a plus b equals 7. Um, hold on. So yeah, like the last few problems, we can add them up, and that gives us 5a plus 5b equals 15. And as a result, a plus, oh, not 15, 35. A plus b equals 7. And then to solve for a and b, we can use this result that we found, a plus b equals 7. So if we subtract that from a plus 2b equals 20, we can eliminate the a, and that leaves us with b equals 13. And plugging this back into this equation gives us a plus 26 equals 20. And that means a equals -6. Okay, so moving on from systems of equations, um, let's talk about some special factorizations. All of these will be available in the handout for future reference. Um, so first of all, if you have a difference of two powers that are the same, then you can factor out an x minus y from it, and then you're left with this sum. And you've probably seen some of the special cases before, such as the um, difference of squares, which is x plus y times x minus y is x squared minus y squared, and also x cubed minus y cubed, the difference of cubes, and um, also x to the n minus 1. You can factor out x minus 1 pretty nicely. Um, if n is odd, then we can also factor out x plus y. So notably, there are the sum of cubes factorizations and the x to the n plus 1 factorization. Okay, and moving on, some other useful factorizations are a plus b plus c squared. So if you multiply this out and distribute it, you should come up with something like a squared plus b squared plus c squared plus 2 times a plus b plus bc plus ca, and something similar for the cube version of it. So these are helpful for finding the sums of powers of roots. Um, and like the example here says, we can find the roots raised to a power n and then sum together using Vieta's formulas and the factorizations above. So that's one application of these factorizations, but they will also come up in a lot of very different problems as well. So, and the other one, which is probably very important and very, very useful if you haven't memorized it or if you haven't seen it before, is Simon's favorite factoring trick. So it's xy plus ax plus by plus ab equals x plus b times y plus a. This is basically just multiplying two binomials together. There are a lot of problems that have this configuration, and you always have to be on the lookout for opportunities to factor an expression into this form. And with this, it can be easy to find the values of the variables. And then a few other ones that are a bit less common, but also still useful. So this is Sophie Germain's identity. And in addition, we also have this one with the sums of cubes, which can be factored in a few different ways. And also the Lagrange abundance of squares formula. So now let's try a few examples that use these um, factorizations. All right, so this is the first example. Does anyone know which factorization we should try to use with this problem? And feel free to send it in the chat. Okay, so if you guessed Simon's favorite factoring trick, you are correct. So notice how there are y squared and x squared, and then they're multiplied together here. So that means we can use Simon's favorite factoring trick to factor this. First of all, let's move the terms to one side and rearrange a little. So we'll start with 3x squared y squared and plus y squared minus 30x squared equals 517. So we can't factor this just yet because we're missing a constant term. But if we just start, we can kind of guess what it is. So it looks like this is 3x squared minus, actually we'll go to the next one, y squared and then minus 10 and plus 1 equals 517. So that means that the constant term is negative 10, and we have to subtract negative 10 from both sides if we're trying to factor it. Someone says they can't hear me. Is anyone else? Is anyone else not able to hear me? Um, Other people can hear me, so okay, we'll keep going for now. So at this point, we have the product of two binomials, and on this side we have 507. And then since x and y are integers, then these two binomials must also be integers. So that means they must be factors of 507. And 507, it can be factored as 3 times 13 cubed. So these two binomials have to be some factors of 507. If you just take a look at it, I think it makes sense for y squared minus 10 to be 39, and 3x squared plus 1 to be 13. Since otherwise they wouldn't be integers. And that gives us y squared equals 49 and x squared equals 4. And overall, we're trying to find 3x squared times y squared. So that will be 4 times 49 times 3, which should come out to be 588, I think. Someone can double check that. Yeah. So this is one example of Simon's favorite factoring trick. Okay, we'll keep moving on. All right, so let's take a look at this example. Does anyone know which factorization we should use for this one? And you can take a look at the list in the handout that Anant sent out. Okay, if you guessed Sophie Germain, that is correct. Let's take a look back. Notice that it's a to the 4th power plus 4 times b to the 4th power equals all this. And that is what we have here. So now, to get started with this problem, there are a lot of numbers, and that can make the problem seem more complicated and confusing than it actually is. So there's something useful we can do here is actually define a few variables. So let's let A equals 2012, B equals 2013, and C equals 2014. And I think the handout might be slightly different, but both would work. Now for the first fraction, we have c to the 4 plus 4 times b to the 4 over, let's see, b squared plus b plus c squared minus a to the 4 plus 4b4 over b squared plus a plus b squared. All right, and I prepared another slide because this would take up a lot of space. All right, so we can factor c to the 4 plus 4b4 into c squared minus 2bc plus 2b 2b squared times a squared, not a squared, oh sorry, c squared plus 2bc plus 2b squared. And then on the bottom we have b's. If we multiply everything out, we should end up with c squared plus 2bc plus 2b squared. Let's just double check. Right. Okay, and that means that the bottom cancels out with this part. And then the other fraction is similar. We'll be left with, we'll also be left with the minus part of this factorization here. And that is equal to a squared minus 2ab plus 2b squared. So now looking at this, the 2b squared cancel. And then we also have c squared minus a squared minus 2bc plus 2ab. And we can do some factoring now. C minus a times c plus a can stand in as a difference of squares for this. And then for this one, we can factor out 2b from both. And that leaves us with 2b times c minus a. Okay, if we look back at our original definitions, c minus a would be 2, and c plus a would be 4026, and then minus 2 times b 2013 times 2. And if you take a look, these two are the same thing, so actually this equals 0. Any questions about this one? Okay, we'll move on. Okay, now let's take a look at this problem. So a, b, and c are real numbers such that a plus b plus c equals 1. And we're trying to show that a cubed plus b cubed plus c cubed minus 1 equals 3 times this quantity here. With this problem, where we're trying to show that a statement is true, we want to start with something that we know is true and try to make it look like the one that we're trying to prove. So
maybe not. Okay, yeah.
okay, so let's look at the factorizations here.
Yeah, finally.
This is the, if you take a look at number 6 here, it looks very similar to the problem that we were just looking at. So let's take this one and see if we can make it look like this. And so that was a cubed plus b cubed plus c cubed minus 3abc equals, what else do we have? A plus b plus c times a squared plus b squared plus c squared minus ab minus bc minus ca. Yikes. It's supposed to be a ca. Okay. So immediately we know that a plus b plus c equals 1. So we can get rid of this because the product will just be this. Next. So at this point, let's go back to the factorizations and take a look at this one. The a plus b plus c squared equals this quantity. Since a plus b plus c squared equals 1, and we also happen to have a 1 here, we can probably take that one and use it somehow to get to the right answer. So the factorization was a plus b plus c squared equals a squared plus b squared plus c squared plus 2ab plus bc plus ca. And it's all equals 1 because a plus b plus c equals 1 squared is still 1. Now, we have a squared plus b squared plus c squared here that we don't want in the final equation. So let's just subtract this equation from the first one and see what happens. A cubed plus b cubed plus c cubed. And at the same time, let's also move this minus 3abc to the other side. It's 3abc. Now the a squared, b squared, c squared, that's all gone now. And we also are subtracting 2 of these ab plus bc plus ca from this one. So in total, that's 3ab plus bc plus ca and minus 1 here. And then we're done basically because this is the equation that we were trying to find. Any questions about this one? Okay. And if I'm going too fast at any point, please let us know and I can elaborate a bit more. Okay. So, oh, I didn't even use the second page. All right, so let's take a look at this checkpoint, and we'll talk about it in 1 to 2 minutes. But first, can someone tell me which factorization would be the best to use here? That you can keep looking and refer back to the list of factorizations, and we'll talk about this one in about a minute. All right. Did anyone have any progress with factoring the equations? Did anyone figure out which factorization to use? Because this should have been Simon's favorite factoring trick problem. So if you notice, all of these have the x plus y and an xy structure. So let's factor each equation with Simon's favorite factoring trick, starting with the first one. If we rearrange stuff a little bit, we have xy minus x minus y equals 11. And of course, we have to add 1 to both sides to factor it. Okay, someone has to go. Goodbye. All right, so let's keep going. We'll have the rest of the recording on the YouTube channel to catch up on later. So using Simon's favorite factoring trick, this becomes x minus y minus 1 equals 12. And the rest of them are very similar to this equation. If you factor them, you should get y minus 1, z minus 1 equals 20 for the second one, and z minus 1 times x minus 1 equals 15 for the third one. So there are two possible solutions, one where the variables are positive and one where they are negative. You can do like factoring, but if you also just look at it, you'll find that the solutions are x equals 4, y equals 5, z equals 6. This is one of the solutions, and the other one that works is x equals negative 2, y equals negative 3, and z equals negative 4. And those are the two solution sets for this system. All right, now let's move on to radicals and conjugates. So if you remember from the complex numbers handout, a conjugate is a binomial such that its conjugate will be the second term negative. So the conjugate of this in this case would be x minus y. And this is useful for um, rational, or not radical number expressions, because if we have, for example, a plus root b, and we multiply by the conjugate, we get rid of the rational. Oh, not the rational, the radical. And that helps us simplify fractions and all that stuff. So let's take a look at this checkpoint and see if you can come up with an answer. Okay, so did anyone get an answer? This one wants you to rationalize the numerator, so let's do that. Root 3 minus root 2 over root 3, we multiply by the conjugate. Root 3 plus root 2, and that's equal to 3 minus 2, and on the bottom we have root 3 times root 3 plus root 2. And that should give the denominator of 3 plus root 6. So if you got that, that was the correct answer. Okay, and a lot of time in algebra problems, or even stuff like geometry problems, there will be some nested radicals, and there's a um, specific way that you can denest them and then get them into a form that's more usable. So for this one, um, a radical under a radical can basically always be expressed as a sum of two radicals instead. So if we square both sides to this equation, we can get a plus b plus 2 root ab equals 10 plus 2 root 21. So that means a plus b equals 10 and ab equals 21. And that gives us a equals 7, b equals 3, or the other way around, but it produces the same result. And that means that this radical can be denested as 7 plus root 3. All right, so give that a try with this radical. And I'll give you a minute for that. And you can send your answers in the chat once you're done. Okay, did anyone get an answer? Should have been root 5 plus root 6. And it's using the same method as above. So in general, um, we can have this theorem in general for denesting a radical. And I won't go over the proof right now to save some time, but it's included in the handout, and you can basically square both sides to get the answer. So it might be a good idea to memorize this, but if not, you can also just do the same method to denest the radical. Okay, so now let's move on to talking about some substitutions. So substitutions are when we substitute in one value for another, but we can also at the same time substitute in a new variable that we create for an algebraic expression, and that can help make the equation that we're trying to solve less complicated and um, a bit easier to understand. So this one we can make the substitution y equals x squared plus 18x plus 30. And that means that this thing becomes y equals 2 root y plus 15. And this is a lot easier to solve now, obviously, because you can just square both sides and get y squared equals 4y plus 60, and it's a system. No, this is a quadratic equation where we can factor it as y minus 10 times y plus 6 equals to 0. So now we have two possibilities. Either, actually, there's only one possibility, sorry. Because the two solutions are y equals 10 and y equals negative 6. But if we look at this equation here, the square root cannot be negative. So that means that y cannot be a negative number. And that means the solution is extraneous. So we focus only on y equals 10. If we plug this back in, we have 10 equals x squared plus 18x plus 30. And solving this gives us is there a way to factor this? Oh wait, never mind. We're trying to find the product of the real roots. Sorry. So if you know Vieta's formulas, then the product is just 20 over 1. Well, you can also find the roots manually using the quadratic formula, and that will also give you 20 as the product. So in this example, substitution helped make everything a lot more simpler and easier to solve. Okay, so let's take a look at this example now. Can someone tell me what might be a good substitution to make? All right, so in this one, we can do x equals this quantity here, y for the other one, and z for the last one. And that gives us x plus y plus z equals 0. Okay, now we can go back to the special factorizations and look at the one that's underlined again. If we take that one and bring it over to this one, we have x cubed plus y cubed plus z cubed minus 3xyz equals x plus y plus z times all of that. But since x plus y plus z equals 0, this is now, all of this is now equal to 0. So that means that x cubed plus y cubed plus z cubed equals 3x yz. However, if we plug in these things again, so oh sorry, let me get my eraser. So a minus b plus b minus c plus c minus a, that equals to 0. So that means 3xyz equals to 0. And notice that in order for this to be true, one of these three variables, x, y, or z, have to be 0. So let's say x equals 0. In that case, a minus b equals 0. So a equals b. And if that's true, then the rest of the equation here also holds, because if you plug in b minus c and c minus b here, they are the same thing but opposite, and they cancel each other out and equal to 0. So overall, it turns out that all A, B, C work. But either A equals B, B equals C, or C equals A. So that would be the solution set for this equation. All right, so let's do this one last checkpoint before we take a short break. We also have another symmetry section, but it looks like we might not have time for that one this week. So let's come back in about a minute to talk about this checkpoint. Okay, did anyone get an answer? It's multiple choice, so you can just guess one. And it might be right. What substitutions did you guys use? Right, someone said C. Right, the answer is C. So if you do y equals x minus 1, then the sum s is y to the fourth plus all this. Okay, and then notice that this is actually y plus 1 to the fourth. And if we plug x minus 1 back in, this is just x to the fourth, or c as an answer. So any questions about what we've covered so far? All right, let's take a 5-minute break. Maybe step away from your screen for a moment because looking at screens for too long is not good for your eyes. And we'll do the start the knockout after um, the break. So let's come back at around 2:03. 3:03, actually, sorry.
这姐你写的，你写的。哦，是谁把这个踢了？啊？为什么他突然 restart 了？
Okay. If you're ready, raise your hand. You can send something in the chat as well. Okay. All right. So before we start, I want to mention the exercise leaderboard once more. So for this week, we're going to have 20 problems, exercises again, and you can submit them through the Google form on our website. So just be on the lookout for more information about that, and you can start submitting problems as after this ends, basically. Okay. So let's go to the rules slide for Zoom lockout. Okay, we might skip the first problem. I don't know. Anyway, so the rules are 2 people face off trying to solve a problem, like in Mathcon's countdown. There's a 1-minute time limit. Whoever solves it correctly first stays in. You can either type your answers in the chat or type or say it out loud if you want that extra advantage. So the other person is out if they don't solve it correctly first, and a new person comes in. If no one answers within the time limit, both people are out. If someone answers incorrectly, they are out, but the other person stays in. Okay, any questions? Okay. So it looks like our first pairing will be Abby and Anna. So let's begin. Can you, Anna, can you type hi in the chat if you're ready? Okay. Let's start.
Can you try reloading the page? I've had the same issue. Okay, seems like it's not loading, and that's probably because we have a video timer, and that is currently not loading for some reason. So we're gonna remove it and have someone time.
I have the same problem. Okay. Sorry for the technical problems. I think we can start now. Let's go. This is the first problem. Sorry. Okay. Did anyone get the answer? Right, that is correct. Okay, so both Abby and Anna are out. Next up is Austin and Jesse. You can type hi in the chat if you're ready. All right, let's go to the next problem. Okay, did anyone else get the answer? All right, the answer was 5. Okay. Next up is Leon and Sabrina. You type hi in the chat if you're ready. All right. Okay, let's start. Okay, did anyone else get the answer? Right, and the answer is 8. Okay, so next up, it looks like we have Lillian and Florence. Can you type hi in the chat if you're ready? And okay, let's start. Okay, did anyone get a different answer? The correct answer was 4. Okay, next up we have Richard and Flora. Right, and Flora, can you type hi in the chat? Okay, let's start. Sorry, that is incorrect. Um, does anyone have another answer? Okay, well, this is the correct answer, root 21. We are, oh shoot, okay. And we're back to Abby and Anna. Okay. Oh shoot, okay. If you're ready, can you type hi in the chat? And Abby, okay, let's go.